Alright, here is example 1. Which of our solving scenarios does this one fit? It could be that we have a base with an exponent on the left and a constant on the right, and then it would fit whichever one that was. Let's look back at our options. So that would be like option 5, where we could take the log of each side. However, upon closer inspection, I don't know if you noticed, but 1 over 16 can be rewritten as 2 to the negative 4 power. Because 2 to the 4th power is 2 times 2, which is 4 times 2, which is 8 times 2, which is 16. And then the negative gives us the reciprocal of that. So if you thought about that for a minute, that the base of 2 and the base of 16 could be manipulated to match, then we can just use the second scenario here with this method we've already learned and looked at previously. So I'm going to go ahead and write this as 2 to the x squared plus 5x equals 2 to the negative 4. At this point, we can use our one-to-one property, which says if the bases are equal, then the exponents can be set equal and solved. So I'm just going to take x squared plus 5x equals negative 4, add the 4 to both sides. We have a quadratic now to solve using the zero product property. I'm just going to factor x plus 4 and x plus 1. Double check that by multiplying it out. So x times x is x squared, x times 1 and 4 times x add up to 5x, and 4 times 1 is 4. Once we know that, we know that x plus 4 would equal 0 to make this whole thing equal 0. So x could equal either negative 4 or x plus 1 would equal 0 if x equals negative 1. So we have two possible answers, negative 4 and negative 1. We don't need to check those answers like we did with logarithms, because the domain of an exponential is all real numbers. So you can check them if you want. There's nothing that says you can't always check answers to an equation that you solve. But there shouldn't be an issue with them becoming extraneous. Let's look at example 2. Example 2 has some extra coefficient numbers that we should probably get rid of. I don't know if you remember me showing this example when we went through these steps, but step 1 to rewrite the equation, one of the main ideas to this step is dividing out any coefficients that are in the way. So we've got both a coefficient of 2 and a coefficient of 10. So theoretically we would want to get rid of the 10, which means we would divide both sides by 10, but then that would give us a new coefficient over here of 1/5, which we don't necessarily want that either. So I'm going to show you how this one works out nicely without having to worry about the fact that those two numbers are different. If we go ahead and divide both sides by 2, we get 5 to the 3x minus 1, and then 5 times 25 to the x. And I don't know if you're noticing all of the 5s, but it looks like we can probably get a common base of 5. 25 to the x can be rewritten as 5 to the 2x. So if we have 5 times 5 to the 2x, that's the same thing as 5 to the 1 plus 2x. Because it's like this one has an exponent of 1, and this one has an exponent of 2x. And when we combine exponentials with the same base, by multiplying them together, we add the exponents. Hopefully you remember that property of exponents, because that comes in really handy in this problem. Okay, now we have our common bases. We can do exactly what we did with our last problem and just set our exponents equal. And then solve the resulting linear equation. This time it's not even a quadratic that we have to factor or anything like that. Add that 1 to each side, so 3x minus 2x gives us plain old 1x, and then add our 1s, we get a 2. That should be our solution.